Question 7 is on the derivative of logarithmic function. So let's try question 7i. So for question 7i, right, let's just show it d dx of ln e to the power of x cosine x. So before I even differentiate this, right, let's use the laws of logarithm and split the logarithm over here. So this will be d dx ln e to the power of x plus ln cosine x. Okay, using the product rule in the laws of logarithm. So now after we split, I encourage you to do the splitting first because that will make the differentiation easier. Then we're going to differentiate it. So this will be d dx of x, because ln e to the power of x, right, using the power law, we can bring down the x. So over here we haven't differentiated yet. So ln e to the power of x, we can bring down the x because of power law, and x ln e, which is equals to x because ln e itself is 1, and then plus ln cosine x. Now we can differentiate this and it's much easier. So this is equals to 1 plus 1 over cosine x times the derivative of cosine x, which is minus sine x. So this gives us 1 minus sine x over cosine x. And we know that sine x over cosine x is tangent x. So this gives us 1 minus tangent x. And shown. We are done with question 7i. So anyway, just to point it out, you can brute force your way by directly taking 1 over e to the power of x cosine x, and then you differentiate e to the power of x cosine x. But I wouldn't suggest you to do that because here then you have to use the product law, and that will be a little bit tedious. So I wouldn't suggest you to do it this way, but eventually you will still get the same answer. I do suggest you use this method, which is whenever you see a logarithm, it is advisable for you to straight away do the splitting if it's possible. So let's move on to question 7 part 2. So using part 1, find the integral of tangent x dx. So we can see that earlier in part 1, right, the result we have gotten is that d dx of ln e to the power of x cosine x equals to 1 minus tangent x. So this means that if we isolate tangent x alone, so let's bring tangent x from the right hand side to the left hand side, and then we bring this to the right hand side. So we get tangent x equals to 1 minus d dx of ln e to the power of x cosine x. Okay, so now using this equation over here, and we are required to find the integral of tangent x dx, right? So we make use of the results earlier in part I, we rearrange it to get this equation, and we can see that it's just tangent x over here, and we are required to find the integral of tangent x. So let's take the integral on both sides. So integral of tangent x dx is actually integral of 1 minus d dx ln e to the power of x cosine x dx, which means that integral of tangent x dx equals to integral of 1 dx minus integral of d dx ln e to the power of x cosine x bracket dx. So integral of 1 dx is actually x, and there's a minus here. So the integral of the derivative of ln e to the power of x cosine x is actually ln bracket e to the power of x cosine x bracket, and then we put the arbitrary constant c over here. So this is the answer. So to explain from here to here, right, basically it's saying I differentiate this, I get something, right? And then I integrate it again, I should get back whatever that is here. So to maybe illustrate this using a simple example, so think about it this way. I'm going to write it on the left hand side over here. So imagine I take d dx of x squared. So this is 2x, which means that the integral of 2x dx is actually x squared plus c, correct? So rather than writing it over here, I can actually from here, I put the integral beside the d dx of x squared dx. Okay, I directly just write x squared plus c. So whatever that's inside, and then finally plus c. So same goes for here. Whatever that's inside, and then plus c. Okay? So that's for question 7II. So let's move on to part 3. Hence, show that the definite integral from 0 to pi over 3 radians tangent x dx is equals to ln2. So this is a question on definite integral. So without further ado, let's try this question on 7 part 3. So the definite integral from 0 to pi over 3 radians of tangent x dx, right? Using the result earlier. So the definite integral, we can ignore the constant c. So x minus ln e to the power of x cosine x, and pi over 3 over here, and 0 over here. So this is actually equals to, evaluating it, substitute pi over 3 inside first into all the x. So pi over 3 minus ln e to the power of pi over 3 cosine pi over 3 minus, substitute the zeros here and here and here. Okay, so we get 0 minus ln e to the power of 0 cosine 0. So this is equals to pi over 3 minus ln e to the power of pi over 3. After keying in your calculator, you will realize that cosine pi over 3 over here is actually equals to, let me take the calculator. So cosine pi over 3 over here is actually equals to 1 over 2. Okay, so this is actually e to the power of pi over 3 over 2. Okay, and then we close it up, we close it with a square bracket, and then minus, and then plus ln e to the power of 0 is 1, cosine 0 is 1, so this is ln 1. Okay, but ln1 is actually 0, correct? So we can write ln1 has 0. So just to let you understand why is ln1 0, because ln1 is actually log to base e of 1, so e to the power of 0 is equals to 1. Okay, so this is actually equals to pi over 3, okay, minus bracket, let's write the square bracket over here, ln e to the power of pi over 3, and then we have our minus ln2 using the quotient rule in the laws of logarithm. So this simplifies to pi over 3. Now, using the power law in the laws of logarithm, okay, we can bring the pi over 3 down. So this is minus pi over 3 ln e. But since ln e is actually 1, so we don't have to write this. And then we have our minus, and minus mean is plus ln2. And pi over 3 minus pi over 3 is 0, so we are just left with ln2, and that's it for this question. We have shown that the definite integral from 0 to pi over 3 tangent x dx is equals to ln2.